Hey everyone, and welcome to the fifth lecture on Calculus 1 by yours truly, Raul. This is part of a playlist I plan on making to cover all of Calculus 1, which, by the way, is essentially the same as AP Calculus AB. Before we begin, I strongly encourage you to pause the video whenever I ask a question and attempt to answer it yourself before continuing the video. Let's begin. With this video, I really just want you to understand three things. First off, whenever we're dealing with limits algebraically, the first step to solving that problem is to plug in the x value that the limit is approaching. Not much else to explain there. Second, there are some limits that really are as simple as plugging in the limit x value, though you'll rarely ever see them in calculus classes. It's good to know though that this is true so that you aren't thrown off when you first see them. Lastly, whenever a limit's value divides by 0, that is, there's a vertical asymptote at that point, you have to check both the left and the right side limit to actually find the limit value. Anyways, let's begin. So although we've been writing f of x after the limit here whenever we're taking the limit of that function, we can actually just write the function name itself after the limit to take the limit of that function, in this case cosine. So like I said in the objectives, the first step to taking a limit is always to just plug in that x value into the function itself. So for this case, we would have cosine of pi, which we all know is just -1. And actually, this ends up being one of those cases where if you just plug in the x value into the limit itself, you get the limit value. And really, this has to do with this concept called continuity that I'll define later in a future video. But for the time being, just know that sometimes when you plug in the x value, you just get the function value itself for the limit. So we can also have cases where we have a constant being evaluated for a limit. And as you can see here, this 7, there's no x written anywhere. It's just completely independent of x. If you think about the graph of a constant, it's just a horizontal line. And if you think about taking a limit of that horizontal line, that's just going to be the same value the entire time. So this limit, since it's completely independent of x, should just be 7, that constant that we see there in the first place. And one last case that we can have is where we don't even have x as a variable. We can have something else as a variable, like theta. Well, from algebra, you know that anything can just be a variable. You can even write a smiley face and have that be a variable. But regardless, we just plug in this value right here. So we'll plug in that pi over 2 into sine. And as we all know, this is equal to +1. So again, it's one of those cases where plugging in the limit x value, or whatever the variable is, into the function gives you the proper limit value. So now let's use that principle from taking limits of just plugging in the x value and see what we get for this. So whenever we plug in 3 into the x here, well, very simply, we get the 2 divided by 3 minus 3, which is just 2 divided by 0. And I guess with limits, you could say that 0 isn't actually a 0, it's like a really small number. So if you divide 2 by a really small number, you get like some kind of infinity. But we have to figure out which infinity it could be, because it could either be positive or negative. So to do that, we have to take the one-sided limits for that limit. So here, x from the left side, right? This little negative is for the left side. If you think about what the left side means whenever we're looking at graphs and coordinates and all, that just means that it's this number, but a little bit more negative. And so what we could try maybe is plugging in something like this. We could try a 2 divided by a 2.99 minus 3. So 2.99 is a number that's really close to 3, but still like a little bit more negative. It's less than. So now if we have this, that ends up becoming 2 divided by negative 0.01. And really this 0.01 isn't really a 0.01, it's just a super tiny number that is negative. So if you think about dividing a number by a super tiny negative number, well, you end up with negative infinity. So this limit here is equal to negative infinity. Now if we try taking the right side limit, well, let's see how that turns out. Whenever we come from the right side, that's just a number that's going to be a little bit more positive. So this time we could do 2 divided by 3.01 minus 3. So that becomes 2 divided by 0.01. And again, this 0.01 isn't really what it is. It's just a really tiny number. In this case, that's positive. So 2 divided by a super tiny number that's positive, that should just give us a positive infinity. So this is positive infinity. So we see that the right side limit is equal to positive infinity. The left side limit is equal to negative infinity. Since they're not equal to each other, well then the limit itself, it does not exist. So that's how you would go about solving one of these problems. Okay, so now let's take a look at this example. So here, we see that things look a little bit messy And it's really not nice to work with it like this. But we see here, this is a quadratic equation. Let's try to maybe factor it. So let's say that if we try to factor that, it actually ends up becoming x minus 1 times x minus 2. And you can kind of check that yourself. So now, well, it's pretty easy to just take the limit this time. If we try to just plug in the 1, well then this x, you plug in the 1 there, and then we end up with 1 minus 1, then we end up with 1 minus 2, and that ends up being essentially a 1 divided by 0. So we end up with that same case that we did last time. So there's some plugging in of the left side and right side limit that we have to do to actually get the limit value. So now let's do the left side limit to figure things out. Again, if we plug in a number that's a little bit more negative than 1, before I did the whole thing where like essentially this would be a 0.99, but now I'll kind of do it a little bit more symbolically. Let's say that this 0.99 is actually just a 1 minus there. So this 1 minus represents a number that is super close to 1, but less than. Let's just remember that then. So again, if we factor everything, we end up with that x minus 1 and the x minus 2. So if we plug in that 1 minus, we get the 1 minus up here, and then we get the 1 minus minus 1. We have that 1 minus minus 2. So the 1 minus by itself, well really that just acts like a 1. So we can just treat that as a 1. And then down here, this 1 minus minus 2, well again, the 1 minus can just really act like a 1 here. So 1 minus 2 is negative 1. But this 1 minus minus 1, again, 1 minus is a number that's really close to 1, but less than. So if you have a small number minus a big number, you end up with a negative number. And the way that we can represent that is with a 0 minus. This is because since 1 and 1 are essentially the same number, this 0 minus is a number that's super close to 0, but still negative, just like we had the negative 0.01 before. And so now we have this negative 1 here times the 0, so this ends up actually becoming a 1 divided by 0 positive, and this is just a number that's really close to 0 but positive because this negative cancels that negative. Now 1 divided by a 0 positive, that just ends up becoming a positive infinity. So the left side limit is a positive infinity. Now if we try the right side limit, again we can factor everything. So we have the x divided by x minus 1 times x minus 2. So we plug in that 1 plus this time. So we get that 1 plus up here divided by a 1 plus minus 1, and then 1 plus minus 2. Again, this 1 plus is essentially a 1, so that'll just be a 1 in the numerator. And then 1 plus minus 2, that's just going to be the same negative 1 as before. And then 1 plus minus 1, well 1 plus is a number that's really close to 1, but a little bit bigger than it. So a big number minus a small number, that's going to be a positive number, and in this case it's going to be a 0 plus. And so again, this negative makes this 0 plus into a 0 minus. So we end up with a 1 divided by 0 minus. And then this, as we saw before, a number divided by a number that's really tiny but negative, that will be negative infinity. So again, the right side limit equals negative infinity, the left side limit equals positive infinity. So since they're not equal, this does not exist. So let's do this last example right here. And again, it's one of those messy polynomials. So if we try to factor it, we actually end up with an x minus 2 on the numerator and an x plus 1 squared on the denominator. You can kind of check that yourself. So let's try to plug everything in. We get a negative 1 minus 2 in the numerator, and we get a negative 1 plus 1 squared in the denominator. And if we simplify everything, we get that negative 3 on top and then a 0 squared on the bottom. But 0 squared, that's just 0. So we end up here with that situation again where we divide by 0, so we have to plug in values into the left side and the right side limit to figure out what the limit value should be. So here let's try to start with the left side. So again, I'll kind of do things symbolically like I was doing the last example, just do that negative 1 minus straight into the limit. So we end up with a negative 1 minus, minus 2, divided by negative 1 minus plus 1 squared. And then this right here, this negative 1 can just act like a negative 1, so that becomes a negative 3 on top. And I'm going to rewrite this using the associative property to kind of make things a little bit more clear. So we have that 1 minus 1 minus squared. So I kind of switched this to here and that to there. So now we can kind of think about this a little bit better. This 1 minus is a number that's the same as 1 but slightly smaller. So if we have a big number minus a small number, we end up with a positive number. And a positive number squared, that's still going to be a positive number. So that ends up being a negative 3 divided by that 0 plus that we were so used to seeing. And of course this is squared, but 0 plus squared is just going to be still that 0 plus. And now we can see that we have a negative number divided by a super tiny positive number, and that ends up with a negative infinity. So now let's try to do the right side limit to finish off this example. So again, I'm going to plug things in symbolically. We have that negative 1 plus minus 2 on the numerator, and we have a negative 1 plus 1 squared on the denominator. So this again on the numerator becomes a negative 3, and I'll rewrite this again using the associative property to make things clear. So 1 minus 1 plus squared. So this time the 1 plus is a number that's the same as 1 but slightly bigger. So if we have a small number minus a big number, that ends up being negative. That's just how subtraction works. And so we have that negative 3 and then the 0 minus squared. But think about this, the 0 minus squared, that minus is going to cancel since it's squared and it's going to become positive. So we end up with that negative 3 divided by 0 plus. And this is the same thing as before, a negative number divided by a super tiny positive number, that should just be negative infinity. So finally we have an example where the right side limit is equal to negative infinity, and the left side limit is also equal to negative infinity, so the limit actually exists this time, and it ends up becoming negative infinity. That just about wraps everything up. If you want the notes for this video, the link will be down in the description. Thanks for watching. Be sure to check out the preceding lectures and let me know of any suggestions that you may have for this video or even the lecture series in general. Have a great day.